I will start recording. So I think we finished till this slide. We were discussing different models which can be used to calculate the amount of radiation falling on a tilted surface. Right, so then we discussed that we can neglect this circumsolar and horizon diffuse radiation, and this equation can be simplified to this form. Now in this equation there are three components: beam radiation, right, then diffuse coming from the entire sky, and we are assuming that is isotropic in nature, means it is uniform from every side, from every direction, that is uniform. And this is the radiation coming from reflection from the surrounding ground and reaching on the surface of the collector. So that's what we covered till this point. Then we also started, I think, this numerical. So I explained how to use those equations. So let's do it step by step here. So
Doctor, if you may allow me, I don't know the other see the screen or no, but it's not visible for me.
Okay, screen is not shared. Okay, sorry.
Me too, Doctor. Me too, Doctor. I thought I have a bad internet.
Now it's shared. Can you see?
Yes, now we can see.
Yes, now. Yes.
Yeah.
All right. Okay, so this is the numerical which we started last time. So using the isotropic diffuse model, right, the one which we just studied, estimate the beam, diffuse and ground reflected components of solar radiation. Okay, so we need to find out the beam component, diffuse component, and the part which is getting reflected from the ground of this solar radiation, and the total. Total means sum of all these on a surface which is tilted at 60 degree. All right. So here we have a surface which is tilted at 60 degree. So that is beta. And the solar radiation which is falling on it, one is directly high beam, second is diffuse coming from the entire sky, okay, and that is ID, diffuse part, and the radiation which is reflected from the ground, the part which is reaching on that surface. So that is I, which is reflected from the ground. Okay. And this collector is sloped at 60 degree, right, towards the south, and it is facing south. So means gamma, which is surface azimuth, that is 0 degree because it is facing exactly south. And the location is 40 degree north. The location of that solar collector where it is placed, the latitude is 40 degree north. So we are in the northern hemisphere, and we need to find out these solar radiations for the hour. So hourly, that's why we are using I here. For the hour of 9 to 10 a.m. between this hour. Okay, so 9 to 10, it means these are omegas or hour angle. So omega 1, 9, and omega 2, 10, 10 o'clock. AM means in the morning, so 9 means from 12, so it's 3 hours, so 15 into 3, that is 45 degree. And it's morning, so that's why negative. Similarly, omega 2, that is 30 degree. In the morning, so that's why negative. On February 20. So it means nth day is given. 51. Here I here means the radiation, available radiation or measured radiation. If there is a pyranometer placed horizontally, so this available total radiation, I without B, D or R, it means it is the total amount of radiation which is falling here. That is measured by that pyranometer. So this measured radiation is 1.04 during that hour, 9 to 10 megajoules per meter square. And the reflectance of ground, rho g here represents the ground reflectance. So the average ground reflectance, rho g, which we would need to calculate that reflected radiation. So that is also given as 0.6. Okay. Okay, so we need to find out this beam, diffuse and reflected radiation when this total radiation falling on a horizontal surface is given. It is given. And we need to find out IB, ID, and I reflected on not on a horizontal but a tilted surface, because this beta 60 degrees given, and the surface is facing exactly south, means surface azimuth is 0 degree, and this is the location. Okay, so first of all we need to find out the beam and diffuse part. Right. In this total I, what is beam part and what is diffuse part? And for that we learned that there is this concept, clearness index, and clearness index is given by I over I naught. Okay, so I is given, I naught is the radiation here. If the same horizontal surface is here outside the atmosphere, so that is I naught. So let's calculate I naught. Then I is given, so we can find out KT. Then KT as a function of I diffuse over I. We have those correlations available. So from there we can find out ID. So first we need to find out I naught. Now this I naught equation, it's given data. Here is that equation. This equation which we saw in chapter 1. So of course these equations will be given as a formula in the exam. So you should be able to know which formula to use for which problem. Okay, so that is the hourly vision falling outside the atmosphere. So here you should know the meaning of each term and just put the values. Nth day, solar constant 1367 watts per meter square, latitude, declination, omega 2, omega 1, which I just explained here, omega 2, omega 1, okay, phi, del. So just put values and find out I naught. Okay. So here, after putting all those values, because we need del, so del is separately calculated for nth day. So this is what day 20th of February. So for this, this del is minus 11.579. So just put all those values in this equation, which is done here. So find out the answer. So answer is this one. So it will be in joules per meter square, but it is written in megajoules by dividing with 10 to the power 6 actually. Otherwise the number is so big. So we are dividing with 10 to the power 6. So that's why this is megajoules, 2.28 megajoules. So 10 to the power 6 is divided here, sorry. Okay. So this is the answer, 2.2865. And you can see that I naught is greater than I. This is the I naught, the solar radiation during that hour outside the atmosphere for the same location during that hour, 9 to 10. That's what we used here, omega 2 and omega 1. Okay. And this must be greater than this one. This is on the ground, right? Okay. Now using this I naught, I is already given, so we can find out KT, clearness index. Okay. This is I, this is I naught. So I naught is much bigger than I. It means the sky is not clear. So here is the clearness index. Then we can relate KT with ID over I. There are equations of KT as a function of this. So in this case, so you will see those graphs and equations which we discussed at the start of this chapter. So for this KT, this is winter, so omega s is less than 81.4. Okay. Omega s, you can check again. There is a separate equation for omega s that will give you ID over I. Okay. So here is that equation. So now KT falls in this range. Okay. So there were two correlations. So any one of them we can use. So this is one of them. So, but our KT is falling in this range. So you put the value of KT here and you will have ID over I. I we already given. Okay. So now we can find out ID, diffuse radiation. Again on horizontal surface. So far everything we are calculating for horizontal surface. So by putting values of KT, so we can find out ID. So this whole equation is multiplied by I also. Okay, so here somewhere in that correlation. So here we are multiplying with I also. So this is ID, diffuse part in that I, in that 1.04. This is diffused. It means the rest is beam. Okay. So now using this, we can find out beam radiation. Total minus diffuse. So that is the beam part. Okay. So now we have IB and ID calculated. I is already given. Okay. And we used I naught. I and I naught to find out these. But all of these are for horizontal because this is given for horizontal. This was given, this is calculated for a horizontal surface. And now we will put it in that main equation of I, but for tilted surface because our surface is tilted. And that equation for isotropic diffuse model, only this is the model which we are studying in this course. That was IB on a horizontal surface, but for a tilted surface, we have to multiply it with RB. Similarly, this is ID for a horizontal surface, but surface is tilted. So for diffuse part, this was the view factor for diffuse radiation. Similarly, this one, the reflected part out of this total, which is falling on the ground, right? This will be reflected by the ground, right? But all of the reflected from the ground, not all of it will fall on the solar collector, which is sloped at 60 degree, only a part of it. So here we had another view factor, 1 minus cos beta divided by 2. So now this is the equation which will give us the total amount of solar radiation falling on a tilted surface, where this is the beam part, the diffuse part, and that is the ground reflected part. Okay. So now we have IB, we have calculated ID. This is beta is given, ground reflectance is given, total I is given, beta given. But now we need to find out RB. So for RB, the equations which we studied in chapter 1. So the equation was this one. For that was actually cos of theta over cos of theta z. All right, and for a surface which is facing exactly south, gamma is 0. So putting gamma is 0 in that general equation, this is the shorter equation. This is what we discussed in chapter 1. And that is the equation of cos theta z for a horizontal surface. So now we have to put the values in this equation RB. So this equation will also be given, of course, in the formula sheet. So I will share the formula sheet for the exam, okay, which you can print. So now just put values, everything is given, phi, beta, del, omega. Now what is omega here? Because here it's a single omega. Our omega is changing from 9 to 10. Okay, so we can take the average of this omega between 9 and 10. So for example, at 9, it was 45 degree, and for 10, it was 30 degree, right? So we can take the average between these two. And this was with minus. So average of this is minus 37.5 degree. So we can take that average omega for this hour to be used in this equation RB. Okay. The rest is all given. Okay. This is slope, that is beta. So just put values. Okay, for the south facing surface in northern hemisphere, this was the equation from chapter 1, putting values to that is RB. Now we can put everything in that main equation to calculate total amount of solar radiation falling on a tilted surface. This is IB, beam part in megajoules per meter square. This is RB. Look, RB will make this whole term bigger because now we are multiplying with a number which is greater than 1. Just by tilting the surface, the amount of radiation falling will increase. Okay, so that's why. So this is a beam part. This is the diffuse part. This is the ground reflected part. Okay, so here is the total amount of radiation falling on a tilted surface. This was given the total amount of radiation falling on a horizontal surface, which is measured. Now using this, we can find out the total amount of radiation falling on the same surface when it is tilted to 60 degree. So here we can see the effect of tilt. By tilting it, you can see the amount of radiation falling has increased from 1.04 to 1.18, right? It's megajoules, so that's why it's not a small increase, it's a big increase in megajoules per meter square. Okay, so this was the numerical. Here he asked us to find out beam, diffuse, and ground reflected parts separately also. So this is beam, this is diffuse, and this is reflected part. So you can write them separately also. Any question? Okay. So now, so far in chapter 1 and chapter 2, now where we are, we started from sun, these radiations which are reaching on the outer surface of the atmosphere, and here is earth, that is atmosphere. So in chapter 1 we calculated this radiation hourly or instantaneously, G naught, or daily or monthly daily average, H naught bar. Okay. In this chapter we included the effect of atmosphere, and this I naught, G naught, H naught we calculated here on the surface of the earth anywhere. I, G, H or H bar. So we have seen the procedure and equations to calculate these on the surface of the earth. Now, because our aim is a solar thermal system, so every solar thermal system is actually consisting of a solar thermal collector, right, which will intercept this radiation. So now on the surface of the earth, if I show it here, this is some surface, horizontal surface anywhere. Now on the surface of that earth, there is that collector, right, tilted at certain angle. Okay, now this collector normally consists of a glass cover or glazing. Then you have that metal sheet, and there are pipes welded in it. Okay, so every solar thermal collector, whether it's flat plate, evacuated tube, or concentrated type, all have these basic components: glazing or glass. Then we have this absorber plate, and behind this absorber plate there are these tubes or passages in which fluid is flowing. Now, so far in this chapter, we have been able to calculate this radiation falling on that surface. It could be I if we are talking about hourly. It will be G if we are talking about instantaneous, or it would be H or H bar if we are taking daily average or monthly daily average. Now we will continue further now of when this radiation is falling on that glass cover, then what happens to this radiation? Because our ultimate goal in this chapter is to find out this radiation, which will be finally absorbed on that surface of absorber. But so far we have reached here on the outer surface of that glazing or glass cover. Now what will happen from this point onwards, this is what we need to discuss. Okay. So when this radiation has reached here, now what happens to this radiation whenever it is falling on any surface, and if this surface is transparent, that's we discussed in chapter 1 at the start. Here is that incoming radiation, which we are saying it is I or G or H. Now it is falling on a transparent solid surface. So a part of it will be reflected, a part of it will be absorbed, and a part of it will be transmitted. So here we are interested to know when it falls on that glazing, how much will be transmitted, how much will be reflected, and how much of this will be absorbed here within that glazing or glass cover. So now we shall see this part. Okay, we already reached here. Now we will see what happens to this radiation which is available, this one. How much of this will be finally transmitted, and then how much of it will be absorbed. That is the next part. Okay. So now we already know whenever radiation which falls on a body, a part of it is reflected, a part of it will be absorbed depending upon the reflectance of that material, absorptance of that material, and transmission or transmittance of that material. So these are the three things which could happen whenever a solar radiation is falling on a body. All right. So the part which is reflected, we are calling it reflectivity of that material or reflectance of that material. So we can define it as the reflected radiation, IR. This is total I. So this IR over I is called reflectance. Similarly, the part which is absorbed, I absorbed of the total I is called absorptance. And similarly, I which is transmitted, this one divided by total is called transmissivity. Okay. And these are the ratios. So the sum of these ratios, rho plus alpha plus tau, will be 1. All of them are ratios, so every value is between 0 and 1, but their summation will be 1, right? Okay, so that is explained here. So that depends upon this. These are called the radiation properties of any material, reflectance, absorptance, and transmittance. They are dependent upon the type of surface, and also they are dependent, their values, this rho, alpha, tau, they are also dependent upon the direction of incident radiation, at what angle the radiation is falling. Look, for example, here is that surface. If the radiation is falling at this angle, now let me define this angle. This is surface normal. Now this angle will also affect this rho or alpha or tau. Okay. If this angle changes, the reflectance or absorptance or transmittance also changes. So it's not a constant value for every surface. These values change for a particular surface when the angle of incident radiation changes. Okay, so for example, if we say the absorptance of black paint is 0.98, which we normally see the values which are available in the book or standard tables, this value is actually when the radiation is falling at this theta equal to 0. When the radiation is falling like this, normal, or when this angle between this solar radiation and this surface normal n is 0, then this absorptance of that black paint is 0.98. If this angle changes, this value also changes. Okay, so it means these radiation properties, alpha, tau, or rho, these ones, they are not only dependent upon the type of material, but also the direction at which the radiation is falling. And there is one more thing, the wavelength. What is the wavelength of that incident radiation? And this wavelength we also discussed in chapter 1. Solar radiation, there is a particular wavelength band, 0.3 to I think 3 micrometer something. So this wavelength also affects this radiation properties, rho, alpha, and tau. Okay. So we can write, but once we write this equation like this, alpha plus tau plus rho is equal to 1, and we are not mentioning the lambda here. So it means this is a kind of average over all wavelengths. But we can write the same equation that tau at this particular wavelength, for example, 0.3 plus alpha at that wavelength plus tau at that wavelength is equal to 1. So it means we are specifying this reflectance or absorptance or transmittance on a particular lambda. Okay. If we are not specifying lambda, it means it is an averaged value over the entire lambda. Okay. So that is explained here. This equation 50 is valid for average properties over the entire wavelength band. But we can write the same equation in terms of particular wavelength. Right. We can write the same. But in this chapter, we'll be using this averaged value over the whole wavelength band. But now we'll see the effect of that direction on these, right? Because we are interested how much of that incident radiation I, how much of it is reflected, how much of it is absorbed, and how much of it is transmitted. So transmitted, we can find out if I know tau, transmittance of that glass cover. And also this tau is a function of this angle, at what angle this radiation is falling. So I need to know what is tau at that theta. Then I will multiply this tau with this I to find out this I which is transmitted. Okay. Okay, so now we'll see some more equations to find out these transmittance, absorptance, and reflectance. Okay. So first of all, let's discuss reflection. So here is the radiation, incident beam radiation of the sun, for example, falling on that glass, on that surface at this angle theta. What is this theta? Incidence angle. And we already know the equation of this theta. Cos of theta as a function of all those parameters, phi, declination, hour angle, beta, and what else? Solar azimuth or surface azimuth. So this is that theta which we already know how to calculate. Now this radiation at this theta is falling on that body. Okay. Now this body, this is for example glass cover, and this is air. So solar radiation is traveling from air. Now it strikes the glass cover. A part of it is reflected and a part of it is transmitted, goes into the surface. And when it goes into the surface, it refracted. So you know from basic physics, whenever a solar radiation or light wave strikes a surface, a part of it is reflected. If it is flat surface, this angle of incidence and angle of reflection will be same, but angle of refraction will be smaller. depending upon this refractive index, right? This is the refractive index of that medium. This is the refractive index of the second medium. If the refractive index of the second medium is higher than this one, then it will be bended in inwards, right? This is the basics of light or electromagnetic waves, which you would have studied in some basic physics. So it is the same thing which we will be repeating here. Okay, so now I want to find out how much of this incident radiation is reflected. Okay, so for that, there are some equations, but before those equations, we need to understand some nomenclature. So this is called incidence angle of radiation. This is called refracted angle of transmitted radiation. This is the part which is transmitted. So the rest is reflected. This is incident, this is reflected, and this is transmitted. The angle of reflection, that is angle of refraction. Here, this is called refractive index. So what is refractive index? If you remember, refractive index, which we represent with n, is equal to the velocity of light at a particular wavelength in empty space divided by velocity in that substance, right? Velocity of light in empty space divided by velocity of light in that medium, for example, air or glass. That is called refractive index. So velocity of light in vacuum divided by velocity of light in that medium. That is called refractive index. So normally air also has the same refractive index as vacuum. So N1 for air is about 1. For glass, this N2 is about 1.5, right? 52. So these are called refractive indexes because we would need these θ1, θ2, N1, N2 to find out that reflected radiation. Once we know reflected radiation, then we can find out transmitted radiation. That's why we are learning all these. Okay, so I have explained this one, this θ1 incidence angle, θ2 refraction angle or refractive angle. These two angles, they are related to each other by this law, Snell's law, how they are reflected using this one. Refractive index of medium 2 divided by refractive index of medium 1 is equal to sine θ1 over sine θ2. And always remember, this θ1 is actually the incidence angle of radiation. We know how to calculate it from chapter 1. We are talking about solar radiation, right? So if I know N2, if I know N1, we can find out θ2 from this equation. Okay, N is clear. This simple N is just the ratio of these two refractive indexes. Refractive index for air is about 1, for glass is 1.526, and for water it is 1.33. Okay. Any question so far? So now we want to find out the reflection. So for reflection, there are formulas, there are expressions developed by Fresnel. Okay, you would have studied somewhere, maybe in photovoltaics course, that is the reflected radiation, this much. And here is the equation to calculate the reflectance. If we know θ1, if we know θ2, then we can find out that reflection. Okay, but now this reflectance has two parts actually, because this solar radiation, it's a light, of course. And what type of light it is? It is unpolarized light. Unpolarized light means it is vibrating in two directions, X, Y, or actually it is vibrating in every direction, right? But for simplicity, we can divide this reflection, because this is when it is traveling, it is moving in every direction. Okay, and this movement in every direction can be assumed for simplicity that it is one of that movement in every direction can be divided into two parts. One is parallel to the plane, and the second is perpendicular to the plane. Okay, for simplicity. Now, what exactly this means? Let me show you here. Okay, so for example, this is the light wave, which when it is moving, it is vibrating in more than one plane. And that is called unpolarized light. Unpolarized light. It's not moving like exactly like this straight line actually. So it is pictured as a straight line, but actually it is moving in every direction. But for simplicity, what we do is that light emitted by sun or lamp or even by a candle is unpolarized. Okay, so it is moving like this, vibrating like this in every direction while it is moving. Okay, so such light waves are created by those electric charges that vibrate in a different directions, and therefore creating that electromagnetic wave which vibrates in a different directions. So this concept of unpolarized light is very difficult to visualize. So in general, it is helpful to picture this unpolarized light as a wave that has average of half of its vibrations in horizontal plane. Okay, this horizontal plane, we assume that half of it is in this horizontal plane and the remaining half of it is in this parallel plane. Just assume a plane here, one is parallel, other is perpendicular. So we are just visualizing that this unpolarized light as a wave that has an average of its vibrations in a horizontal plane, and the remaining half is vibrating in the vertical plane. So if this is horizontal, then this is vertical. Okay, so this is the light when it strikes. Now part of it is reflected. Okay, so when it is reflected, again we are dividing it into two parts. One is parallel to the plane, other is perpendicular to the plane. This one is perpendicular. So this is just an assumption, and this assumption is not something which is not proved. That is a valid assumption, and that gives this assumption gives uh, correct results, error-free results. For most engineering purposes, this is a valid assumption to visualize light like this, consisting of two parts. Okay, so here is that theta I, incident radiation, that is reflected radiation, that is the refracted radiation. Okay, so the same thing is shown here. So here is the light which is assumed to be consisting of two parts. One is perpendicular to the plane, one is parallel to the plane. Okay, so after reflection, again it will have two parts, the reflected part and perpendicular to the plane, and reflected part parallel to the plane. So similarly, the part which is transmitted, it also has two parts. One is perpendicular to the plane and one is parallel to the plane. So let me go back. So here is that equation to calculate that reflected radiation for perpendicular part. Similarly, the reflected radiation for the parallel part. So if we know theta 1 and theta 2, which we can calculate here, if theta 1 is given, I can calculate theta 2 from equation 52. So once we know theta 1 and theta 2, I can use these two equations to find out the reflected radiation. Okay. Now, what is the total reflection? It's just considered as the average of these two, right? Just take the average of these two. This will give us the total reflection. Okay. So this assumption is correct if this light, which is falling, this solar radiation on a surface is unpolarized, right? If the light is not unpolarized, means partially polarized, right? Then this assumption is not correct. That assumption, this equations, Fresnel expressions, those are valid for unpolarized light when it is striking a surface, right? Like solar radiation. Okay, so these are the equations to calculate the reflectance of that medium. When the radiation coming from medium 1 strikes this medium 2, the part which is reflected, we can calculate from here. Okay. If this angle of here, angle of incidence is theta 1, not 0. But if this angle of incidence is 0, if light is striking the surface like this, then then the equations are different. Okay, for normal incidence, right? For normal incidence, when theta is 0, theta 1 is 0, so it will strike and a part of it will be reflected in the same direction. So the same theta 1 when it is 0. So then we have that equation for normal incidence. It is only a function of refractive indexes of medium 1 and medium 2, only based on this. So this equation only when this theta is 0. And we know this theta throughout the day it's changing. There will be a time, for example, at 12 noon, when this theta will become 0. Otherwise, this theta is non-zero. Okay. And if one of the medium is air, okay, so then the same equation, if one of the medium is 0, then this is reflection. When the radiation falling at 0 angle and one of the medium is air, n is equal to 1. Okay. Okay, so this was just the explanation of this perpendicular and parallel part, and here are the equations to calculate reflectance. So once we know the reflectance, then we can go further to find out the transmittance. Okay. Now, we just saw how to calculate this reflectance in this previous slide. Here is that glass cover on which solar radiation is coming, and part of it is reflected. So we saw those equations, how to calculate this reflectance. Now within this glass cover, uh, after reflection, this part which is left will be transmitted. So for example, this is 1, so 1 minus R is transmitted. Okay. Now the same phenomena occurs on the other face, because this glass cover or whatever material, transparent material which we are using, it has certain thickness, right? So now this radiation which is transmitted, now it will finally come here, and now again here the same phenomena will occur. A part of it will be again reflected, and the part will be transmitted. The same thing which was happening here, now the same will occur on the other face, because this glass cover has two faces. There is certain thickness. This is the thickness of that glass cover. So this phenomena is shown here. Okay. So this is incident radiation. Let me show it again. For example, the total amount of radiation which is falling on that glass cover is 1. A part of it is reflected, R, here. Now 1 minus R is transmitted. Now this 1 minus R is traveling. Finally, it reaches the other face. At the other face, again, a part of it will be reflected depending upon what is the reflectance of that material. So this 1 minus R is again multiplied by R. This is reflected. Okay. So this is reflected. So this was the total minus this which is reflected. So this minus this will be transmitted coming out of the glass. Right. So this is, so I can we can say this is 1 minus R, which is incident here. A part of it is reflected. So 1 minus R into R. So which is reflected is this one, 1 minus R into R, because that is the reflectance of that material. So what is left? 1 minus R plus R square, right? So it is equal to 1 minus 2R plus R square. That is actually 1 minus R whole square. That is the part which is finally leaving that glass cover. Okay. Now this part which was going here, again the same thing will happen here. A part of it will be reflected. So this whole thing multiplied by R. So this becomes R square. Okay. And so this minus this is going into the ambient, right? Because this was traveling, part of it is reflected, the rest is again transmitted. So now you can repeat the same thing here again. Now this multiplied by reflection, again R, this will be go here. Now this minus this is what is coming out of that glass. So such pattern is repeated over the whole thickness and length of that glass cover. Right? For example, this is the total glass cover length. So the radiation which is falling, now this pattern is repeated. Okay. So the total, this is the total which is transmitted through that glass of thickness, for example, T. And we are interested to know what is this much, how much is this one. This is finally transmitted out of this total one. So we just need to sum all these. And this pattern is repeating indefinitely. So this, if you look at this pattern, it is 1 minus R square. Here 1 minus R square into R square. And then 1 minus R square into R4 and so on. This pattern is repeating. Okay. And this R is going to the infinity because this R4, then R6 and so on. So this is what we are looking for. We need to sum these, all these, to find out the total amount of radiation which is transmitted. Okay. And again, there are two components of this radiation. One is parallel, one is perpendicular, because this R again consists of two parts, R parallel, R total. All right, so we can write these equations for both parallel part and perpendicular part. Okay, so here you see the part which is transmitted is this one, perpendicular part and parallel part, and this is repeating R square or 4 and so on up to how it is repeating 2, then 4, then 8 and 16 and so on. So that's why it is r to the power n, and you have to sum all this because this 1 minus r square is common. So that is taken out into sigma of n is equal to 0, because here n is equal to 0 to infinity. The same we can write for the parallel part. We can, because we just discussed that this radiation can be divided into two parts. One is parallel to that plane, and other is perpendicular to the plane. Okay, so now if you solve this series, this is geometric series, if you solve it, this will reduce to this form. So there is a complete mathematical steps, which if you are interested, you can see. Just put it in GPT or in any AI software, so it will give you the complete derivation. So this will come out to be this value, which we can further write it, this 1 minus r whole square. So 1 minus r whole square can be written as 1 minus r, 1 minus r, and in the denominator it is 1 minus r square, which we can write as 1 minus r into 1 plus r. So this will cancel, so it is simply given by this one. So this is for perpendicular part, this is for parallel part. Okay. So we already saw the equations to calculate these two. They can be calculated from Fresnel correlations, right? And they are actually a function of θ1 and θ2. So θ1 equation from chapter 1 we know. Okay, if we know n1 and n2, we can find out θ2. So once we know θ1 and θ2, we can find out r parallel, reflection parallel, and reflection perpendicular. Once we know these two, we can use these equations to find out now transmitted radiation. This one, this total transmitted, parallel and perpendicular. So what will be the total transmitted? Just take the average of this one. So total transmitted will be equal to transmitted perpendicular plus transmitted parallel divided by 2, which is written here. Just like we calculated r, total r, as r of perpendicular plus r of parallel divided by 2. Okay, so here this is the transmitted radiation, but why there is subscript r? Subscript r means we assumed in this derivation of this transmitted part of solar radiation that there was no absorption here in this part. What is this part? That is the thickness of that glass or glazing or transparent solid. Here, no absorption. We assumed there is no absorption. There are only reflection losses. Reflection here, here, here reflection, here reflection, here reflection on every interface between two mediums, air and glass. We assumed only reflection, and we said there is no absorption. So it means this transmitted radiation formula, which is this equation 60, it is based on the assumption that only reflection losses are occurring. Okay, there are no absorption. There is no absorption of this radiation when it flows through that glass cover. Okay, so be careful that this equation 60, which is written as tau with r, it means only reflection losses are considered. Absorption losses are not considered. Now we can further go to now this equation which we have derived, that is for one glass cover. If there is only one cover, one glazing. But in some solar collectors, we use multiple glass, more than one glass covers. There is this glass cover, then we can have another glass cover. In between, there is air. And then we have that metal plate. At the bottom, there are passages. So in some solar systems, we use two glass covers. Glass cover 1, glass cover 2. So this equation which we have derived, that is for one glass cover. But again, if there is another glass cover, so the same phenomena will be occurring here. So for two glass covers, or maybe there are 3 or 4 or n number of glass covers, the general formula is like this, which is shown here. If there are n number of glass covers, so here you see n. If there is only one glass cover, so n is 1. If there are 2, so put 2 here. If there are 3, so put 3 here. So that will give you transmittance of n number of glass covers, right? And R, again, here you see this R means only reflection losses are considered, right? And instead of using these equations, we can use a chart. This chart is developed. So from this chart, we can directly read these transmittance values instead of using these equations. If we know the angle of incidence, what is that angle of incidence? θ1. Okay. So if this angle of incidence is known, then we can find out if it is one glass cover, two glass cover, 3 or 4. For 4 glass covers, these are the 4 curves. So as the angle of incidence, now what is this angle of incidence means? This angle, this is, for example, glass cover, that is its surface normal. So this angle, theta, as a function of this theta, what is that transmitted part? When only reflection losses are considered, either use this equation or use this chart to find out transmittance. And you can see after 60 degree, when this angle, here it is 0, now here is, for example, 60. After 60 degree, when this angle reaches here, transmittance drops significantly. So up to 60 degree, so or maybe around 50 degree, this change in transmittance is not that great. But after that, it suddenly drops, the transmittance of glass cover. Okay, any question so far? So this equation 61 is giving us transmittance, and I told you when only reflection losses are considered. But there are some absorption, because when the solar radiation is falling on that glass cover, okay, part of it is reflected, a part of it will be transmitted, this one, but some of it will be absorbed here within that glass cover. If thickness is more, there will be more absorption, right? And some glass covers which are not very transparent, those greenish or brownish glass covers which we see in buildings, their absorption is much more than simple clear glass, right? So in that case, what we have to do, we have to develop another equation where we will find transmittance when absorption losses are also considered. So this equation is transmittance of solar radiation when only reflection losses are considered. Now we shall see another equation to calculate transmittance, transmissivity of a glass cover when absorption losses are also considered, right? So for that we have another equation which can calculate the absorption by glazing, or we can find out the transmittance by considering the absorption losses, and that is given by that law, Boyer's law. I don't know what is the exact pronunciation. So this is a law. Now what this law says, the radiation which is falling on a surface, for example, here is surface, that is the radiation falling on that surface, I at an angle, for example, theta 1, right? And once it will go into that medium, which is glass normally, so this angle will change. This is theta 2. Once it will come out again from glass to air, so it will again change its angle. So this angle and this angle will be same, because here it was air. When it goes from air to glass, it bends towards the center, but when it goes from glass to air again, so it bends away, because here this is N1, this is N2, and this is again N1 refractive index. Okay, so now when this radiation is, a part of it is reflected, but the part which is flowing through this glass, a part of it will be absorbed here also. So now we want to find out what is that absorbed part. Okay, so this absorbed radiation is represented by Di, and that is proportional to the local intensity. Local intensity means total I. So this Di, the absorbed radiation, is directly proportional to incident radiation, and the distance x which it will travel from here to here. This is the total distance x which it will travel within that medium. So it is directly proportional to these two, right? So we can introduce the constant of proportionality that comes out to be k, I, and x. All right, and the intensity of radiation is dropping, right? So that's why there is also a negative sign. So k is the proportionality constant that depends upon the material of that glass, and that is called extinction coefficient. And that depends upon the type material of that glass, or material of that solid or transparent, semi-transparent material. Okay, so some will absorb more, some will absorb less, so that is dependent upon the material of construction that is defined by this K. So this is the absorbed radiation that is directly proportional to the amount of incident radiation and the total distance which it will travel from within that material. Okay, so now if we want to find out the total transmitted radiation after this absorption, so now we have to integrate this equation. So we can integrate this equation. So now I can write this equation as Di, which is absorbed, divided by, let's take this total I here, equal to minus k. What is left is dx. So let's write it in differential form. Dx is the path, the change, or the thickness of that glass, the differential thickness. Okay, so now what is this? This absorbed divided by total incident available. That is called transmittance. That is what we call transmittance when only absorption losses are considered, when only absorption losses are considered. We are not considering reflection losses. That is done separately. We already calculated transmitted when only reflection losses were considered. Now we are calculating transmittance when only absorption losses are considered, and that is defined as the amount of radiation which is absorbed divided by the total radiation which is incident. That is this term. So we have written this equation in this form, and that is representing the transmittance. Okay. Okay, so now we have to integrate, because the radiation from this point till this point, from here till here, it was total I, and the part which gets absorbed. And on the other side, this thickness is changing from 0. Here it's 0, but here it is x, 0 to x. Now what is this x? Okay, let me show it separately here, or let me. So if this is x, the total travel inside the medium, and this is the angle θ2. And what about this one? This is the total thickness of the glass cover. For example, that is L. All right, this one is L. So I can write the equation of x in terms of total thickness L. So just see that triangle. So I can write this x is equal to L over cos θ2. Or in other words, cos θ2 is equal to L over x. So from here, I can write the equation of x. So I can replace this x is equal to L over cos θ2, because θ2 I can find out from θ1 from Snell's law. L is the total thickness of that glass cover. Okay, so now if we solve this equation, so this term is representing transmittance, because that is actually the I which is absorbed divided by total I. All right, but that is log. Okay, ln of, because this is di over I, so that integral is ln, natural logarithm of I. And then if you apply these limits, is equal to minus k. Here it will be x. Okay, and x limit is from 0 to L, so it will be minus kl over cos θ2. Now if you take this ln on the other side, this is left, that is transmittance when only absorption losses are considered. When ln goes there, then it is e to the power minus kl over cos θ2. So now here is that correlation of transmittance when only absorption losses are considered. So this is also done here. This was the basic equation to calculate absorbed radiation and a differential thickness given by Boyer's law. So this equation, so all these terms, K is the proportionality constant. I told you what is this x. X is changing from 0 to cos θ2, so that is explained here. Okay. So by solving this equation, we can have that equation of transmittance when absorption losses are considered here. So here is that equation to calculate transmittance. And here subscript A means only absorption losses are considered. The previous equations in the previous slide, we have transmittance when only reflection losses are considered. Okay, so now we have two equations to calculate transmittance when only reflection losses are considered and when only absorption losses are considered. Okay, so this equation is a function of these parameters. L is the thickness of that glass or that glazing. K is the proportionality constant that depends upon the material of that transparent material, right? For glass covers, this value ranges from 4 per meter to about 32 per meter for different types of glass covers. This is the value of K, extension coefficient that is called. And theta 2 is clear, that is the angle of refraction. Okay. Okay, so all these terms are clear. Now, we have seen equations to calculate transmittance when only reflection losses are considered. We have seen another equation to calculate transmittance when only absorption losses are considered, right? But what about the correlations in which both losses are considered, both reflection and absorption losses? What will be the transmittance of glass cover when both reflection losses and absorption losses are considered? That is given by this person, Siegel and Howell, that gives these equations. The transmittance by considering both reflection and absorption losses. So here is the transmittance of perpendicular part of that radiation. So here is the transmittance involving only absorption losses, which we just saw, Boyer's law. And these are again the reflection part. So here is that equation which gives us the transmittance when both reflection and absorption losses are considered, and that is given only for perpendicular part. The same we can write for parallel part. Just replace this perpendicular with parallel, then take the average of that. That will be the total transmittance. So this equation is for transmittance, this equation is for reflectance. Okay, so here the individual values should be clear. That is that reflection from Fresnel equation, that is transmittance with subscript alpha, that equation which we just saw, minus KL over cos theta, minus KL over cos theta. All right, e to the power minus, that is, so that this equation is for reflection, this equation is for absorption. So it is transmittance, reflection, absorption for perpendicular part. Same we can write for parallel part, right? Same equations for parallel part. And what will be the total transmittance? Tau perpendicular plus tau parallel divided by 2. Okay. Parallel means here replace all these perpendicular with parallel. So there are so many equations, and you can see we are not deriving them. So you can see if we have to derive all those, so the amount of work which we have to do. Okay. Okay. So now this equation, normally this term transmittance when only absorption losses are considered. This is normally typical value is 0.9 for glass covers, and reflection is normally only 0.1. All right, maximum normal glass covers which we use in solar thermal systems, they transmit maximum and they reflect very minimum. So this transmittance of single glass cover, instead of using this complex equation, we can use a simple equation, simply this one, to find out transmittance. Instead of using these complicated equations, simply calculate transmittance by including absorption losses and calculate transmittance by assuming reflection losses. Just multiply these two, that will give us the transmittance, which we can use. Okay, but that is only valid for the covers which are used in solar collectors, not for other applications, because for solar collectors we use glass covers which have very high transmittance and very low reflectance. So then we can use this assumption, this simple equation. Okay, then let me finish that part, then we'll take a break. Okay, so this is the second equation which we saw, absorption, how to calculate the absorption. So here again we can neglect this part because this R is very small, 0.1. So if you put 0.1 here, this is 0.1, this is 0.9, you will see this value comes out to be near to 1 or in 0.9 something. So we can neglect this part. So we can simply say the absorption is simply given by this equation, this part. All right, we can assume this by neglecting this part. Similarly for reflectance, once we know absorptance, once we know transmittance, so reflectance is simply given by 1 minus this minus this. Okay, so we calculate transmittance using this equation, absorption using this equation, and 1 minus alpha minus tau will give us reflectance. Okay, or use this one equation, that simplified equation. Okay, tau when only absorption losses are considered, and this is the total tau. Right, this is reflectance. So for two covers, if there are two glass covers, then these are the equations. Then we have to calculate tau1 for glass cover 1, tau2 glass cover 2, rho 1, rho 2, tau1, tau2. So then for two glass covers, that is the total transmittance, and that is the reflectance. But we are interested mainly in the transmittance. Look, what is tau1 here? Tau1 is actually this one, tau of alpha 1 and tau of R1. Right. Now what is tau of alpha 1? This equation we just saw, Boyger's law, minus KL over cos theta. And what is this one? That is from the Fresnel equations. We derived that equation from Fresnel equation. In this part involves those R1, R parallel, R perpendicular, and then take their average. And what are those R's? Those R's are from theta 1 and theta 2 Fresnel equation. So there are significant calculations involved here. Similarly, this one was simple, was simply e to the power minus KL over cos theta 2. Okay, so just multiply these two, that will give us tau 1. Same you have to do if there are two glass covers. All right, so we can find out tau 1, then tau 2, then use it here to find out the total tau. So this is a huge amount of calculations here. Right, so but there are charts available. We can use those charts instead of using those equations. So far we have seen so many equations. Look, 71 equations so far. So now we will solve one numerical. So this will clarify how to use these equations to solve practical problems. Okay, so let's take a break and then we'll do one numerical, this one. So this will clarify how to use those equations to actually calculate the transmittance, absorptance, and reflectance. Okay. Okay, stop the recording first.